we're going to follow up our last video by looking at a few more examples of sequences. Let's take a look at these examples. All right, first example. Consider ace of k, which is 2 plus the quantity -1 to the kth power. Let's find the first 4 terms in the sequence for ace of k and then show it graphically. So we get started by plugging in k is 1. If k is 1, then we get that a1 is 2 plus -1 to the 1 power, which is 2 minus 1, which is 1. Hence, a1 is 1. If k is 2, we get that a2 is 2 plus -1 squared, which is the same as 2 plus 1, which is 3. Hence, a2 is 3. What about when k is 3? Well, we get that a3 is 2 plus -1 cubed now, which is the same as 2 minus 1, which is 1, just like a1. Hence, a3 is 1. And then finally, the fourth term, k is 4. That gives us a4 is 2 plus -1 to the 4th power, which is 2 plus 1, which is 3 again, just like a2. Hence, a4 is 3. So we see the pattern here. We could just say, well, look, based on all this, what is this sequence in general? It's going to start with 1, then 3, then 1, then 3, then 1, then 3, and so on. So it just goes back and forth between 1 and 3. And that is because of the -1 to the k power in the explicit formula for ace of k. Now, let's try to show this graphically. We see down here a little plane given to us where the inputs down here are k on the horizontal axis, right? So we're plugging in k's into ace of k's. And then the vertical axis, the outputs, these are really our ace of k's. Now, we mentioned in the previous video that we can think of an explicit formula for ace of k, kind of like a function, except the function itself is not continuous anymore. Rather, it's sequentially defined. So it's only defined for the values, in this case, k is 1, k is 2, k is 3, and so on. And so we'll just see some dots appearing in our diagram. Let's go ahead and plot these. If k is 1, we found out that the output was 1. If k was 2, the output was 3. If k was 3, the output was 1. If k was 4, the output was 3. And then it's just going to keep doing this forever after. We don't connect the dots because that would then mean that this ace of k is defined between the values of 1, 2, 3, and so on, but it's not. They're just defined at 1, 2, 3, so on. That's why we just see this graph here is just a bunch of dots. In this case, 1, 3, 1, 3, 1, 3, and so on. So there's an example of just finding some of the terms in a sequence given the explicit formula and then actually graphing it as well. Let's take a look at an example of a recurrence relation. So in this next example, we would like to consider the sequence ace of k where a1 is assumed to be 4, and then the sequence is defined recursively where the next term, ace of k plus 1, is the previous term, ace of k squared, and then minus 2. So let's find the first 4 non-zero terms in this sequence. Okay, starting with k is 1. Well, we're already given what the first term is, and that is a1 is 4. So that wasn't so bad. How about the next one? What about when k is 2? Well, if k is 2, then we're going to get from the recursive formula there above that a2 is the same as a1 squared minus 2. a1 was 4, so this is going to be 4 squared minus 2, which is 16 minus 2, which is 14. Now we're going to use that 14 to find the next term. When k is 3, we get that a3 is the same as a2 squared minus 2, which is the same as, we just found that a2 was 14, square it, minus 2, and 14 squared minus 2, you can punch it in the calculator if you need to, ends up that's 194. And then finally, when k is 4, we get that a4 is the previous term, a3, 194 squared minus 2. Definitely going to probably need a calculator on this one. That ends up being 37,634. So there's an example of how to find some terms using a recursive relation, a sequence defined recursively. Finally, in this last example, just to get a few examples out of the way here before we start talking about a new topic, let's consider the sequence we're given here: 1, 4, 9, 16, 25, so on and so on and so on. And so we notice that 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, and 25 is 5 squared. So this sure seems to be the sequence of the square naturals. And indeed it is. That can easily allow us to find the next 3 terms in the sequence. So we went all the way to the 5th term there in the sequence that's given. So the next one would be a6, 6 squared, which is 36. Then after that, a7, 7 squared, which is 49. And then a8, 8 squared, which is 64. So we can now ask the question, what's the explicit formula for the general term? And hopefully we see at this point, based on what we've done already in this example, that a sub k really should just be take that index k and square it. So there's a few quick examples to transition from the introductory video into the next video. And in the next video, we're going to talk about what it means for a sequence to converge or diverge. All right, that's it for this short video. Stay tuned. Watch the next video. Bye-bye.